Hello class, this is Tim Tomlanovich. Hope you're doing well. Welcome to Water Technology. This is Learning Plan 1. So what I plan on doing here is going over my water technology, and I'll go over the example problems. Then you can discuss your homework or complete your homework. Then next week, Tuesday, I will be online if anybody has any questions to go over the homework. So with that, I will get started. So learning plan 1. Okay. All right. So actually, I'm going to exit out of this. Just kind of do it this way. All right. So environmental technology. So what is it? Environmental technology: drinking water treatment, wastewater control, stormwater control, solid hazardous waste disposal, air and noise pollution, and general sanitation. Okay, so in this class, we touch on a lot of environmental things. We don't focus greatly on it, but enough information for you to function as a civil engineering technician to have enough knowledge of all this. So what is environmental technology? The practice of environmental technology encompasses two objectives: public health protection, environmental health protection. Okay, public and environment. That's the purpose of environmental technology. So as you always hear horror stories back in the 50s and 60s, you see things being discharged into an environment, hazardous waste barrels. So we don't want to be doing that anymore because that's affecting our groundwater, air pollution, etc. So there are a lot more environmental regulations to help prevent this stuff from happening. So it's going to take time. I recommend reading Chapter 1. It's a really great timeline history of how things have occurred over time. So when you look at from the 1800s, realize direct connection between contaminated drinking water and disease. That was in the 1800s. So 50 years later, sewers began replacing sewage cesspools, and then in the 1850s was the first sewer network. Okay, so if we go from 1850 to 1900, we finally figured out from 1900 that 250 reported waterborne disease outbreaks each year, no chlorination plants. So we figured the wastewater, but in the 1900s we're figuring water was contamination. So by the 1960, 9,000 chlorination plants were built. Okay. So we're only in the 2000s. So literally 1900s, that's 100 years. So about 150 years, which isn't that long if you think about it, is before we started realizing contamination of drinking water and waste was an issue. All right. So we are still in the process of making things better, and there are still communities that need their systems to be upgraded. So 150 years, this whole timeline history has been in place where we started worrying about this stuff. So it's not that old. Some major policies. 1970 is the National Environmental Policy Act, NEPA. National policy maintain conditions under which humans and nature can exist in productive harmony and fulfill the social, economic, and other requirements of present and future generations. So that was a big act that was formed by Congress. Then the National Environmental Policy Act. Oh, same thing. Introduced concept of environmental impact statements. Created the Environmental Protection Agency, EPA. Okay. Environmental impact statements, those are key. So when any kind of development now, anywhere, there's an environmental impact statement. I mean, could it be, depending on the structure, groundwater, water, air pollution, waste, how by building that site, how is that impacting the environment? So I think a good one is the Cabela's, the new Cabela's. So if you remember Cabela's, where that was actually built in a wetland. You know, you see all the cattails right on the side of the highway. Okay, so that was a huge controversy about why are we building this, you know, store in the middle of wetlands. So that was an environmental impact statement. So it's my understanding for them to build in those wetlands, they had to create twice as many wetlands to replace what they destroyed. So that's kind of what goes on as all this information goes on, you know, environmental impact statements. And then of course the EPA is helping control regulations of power plants, water systems, etc. Okay. All right, so that was a little background on environmental. So let's talk about hydraulics. Hydraulics is the study of water at rest and in motion. Okay, hydraulics. Now let's move into pressure. Pressure is defined as a force per unit area. So in statics, P, that is pressure, is that force, remember that can be a weight, the unit weight of water, divided by an area. Okay. So P stands for pressure, force, remember what a force is, that's in pounds or kilonewtons, okay, divided by an area. So in US units, typically it's in pounds per square inch, PSI. In metric, it's in newtons per square meter, or that is called a pascal, PA, pascal. Okay. So a little bit of conversion here. 1 pascal equals 0.000145 psi, pounds per square inch for conversion. So we know 1 kilopascal equals 1,000 pascal. The number of pascals a newton per square meter, which equals 0.145 psi. Okay. So hydrostatic pressure depends only on the depth of water above the point in question. So we've all been in a swimming pool, and the deeper you go, the more pressure you feel in your ears. Okay. So when you're in a pool, say you're on the bottom of a 10-foot pool, you're only feeling 10 feet of pressure. It does not matter if you walk horizontally on the bottom of the pool, just walk on the bottom of the pool, okay, that pressure stays the same no matter where you are in the pool, in the ocean, in the lake. If you're 10 feet below the water surface, that pressure is the same laterally, no matter where you are in the ocean, okay? Does that make sense? So hopefully that makes sense. So the deeper I go, the pressure goes up. So increases in direct proportion to the depth. Why is that? So as we get deeper, the pressure increases. Okay, let's think about this. So now we got to use blue for water. All right. So this is our water surface. Okay. So we know 1 cubic foot of water weighs 62.4 pounds per cubic foot. There's 1 cubic foot. There's 2 cubic feet. There's 3 cubic feet. 4. Okay. So right at the surface is 0. So as I get deeper, I keep adding 62.4 plus 62.4 plus 62.4. It gets deeper. So it is a linear direct linear relationship. So basically, how do I figure out the pressure at a certain depth? You take the unit weight of water times the depth, how deep you are in the water. And again, for this one right here, no matter, so I'm on the bottom of my 10-foot pool. If I am standing here versus standing over here, and if I'm 10 feet below the water surface, the pressure does not change. Okay. So the third point is the same at all points of equal depth at a continuous volume of water. Okay, so if the water is connected, Okay, so let's do this. Let's make a pool. And let's say I have a pipe. Okay, and then I have another pool. Okay, here's a water depth. Here's a water depth. Okay, so if this is, let's pretend that this is open. So no matter what, because this is connected, so if I'm standing here or here, because this will cause equilibrium, the pressure is the same. Even when I go through the walk through the pipe here, the pressure is the same because it's continuously connected. So basically, water finds itself in equilibrium because if it's open on both ends, if there's no valve here. So basically, once that happens, so no matter where I'm standing, the pressure is the same on both sides in the pipe, in each of the pools. It's the same if I'm at the same elevation below the water surface because it's continuous. It's finding equilibrium. Okay. And then the last one is acts in all directions at the same point, magnitude, and any direction. Okay. All right. So if I am 10 feet below, here's me standing in the water. Okay. Acts in all directions. Remember the line of actions? Does this look familiar? Force vectors. Same magnitude. So at this depth, 1, 1, 1, 1. And at my... So the pressure is the same in all directions. So these are my senses at the same depth and same magnitude in all directions. Okay. So it doesn't matter if it's horizontal, vertically, up or down or anything. So it's the same pressure. Okay. So here's something that this explains that. So if I look at this gauge, you notice the needles, the needle here, here are the same. So as you look here, so the pressure is up here, the pressure is going this way, the pressure is going this way. As you can look, so it's in the same direction. No matter how that funnel is placed, it's measuring the same pressure. So it acts in 360 degrees. Okay, hydrostatic pressure, so formulas. So this is in metric, 9.8 times H. Okay, H is in height. Okay, and this is in meters. So this is the metric. All right. So what they did is this 9.8 and this 0.43 is they converted it, because remember 62.4 pounds per cubic foot is the unit weight of water, or 9.81 kilonewtons per cubic meter for metric. What they did is, because pressure in the US system is PSI, pounds per square inch, and this is pascals, what they did is they converted that to get it into these units. These are different units. So that's all it is a conversion. This 9.8 is a constant conversion. So this is the metric. This is the English. Okay. H in metric, so it has to be in meters, and English it has to be in feet. Just remember that. So these formulas here. Okay. So if the liquid is not water, you must multiply the pressure by the specific gravity of the liquid. So this is not in your book, but you should remember what specific gravity of water is. Sg of water is 1. Remember, it's the unit weight in relationship to the unit weight of water. Okay? So remember, the specific gravity of water is 1. So if the specific gravity is less than 1, it's floating. So, and if it's greater than 1, it's sinking. So remember, in soil mechanics and cemented ags, we had specific gravities of 2.65 around. Okay, so basically what it's saying is it's in relationship how much lighter or how much heavier it is in relationship to water. So just keep that in mind. I mean, we're not going to go into too much detail about specific gravity, but this formula here is assuming it's water and our specific gravity is 1, because different fluids have different specific gravity. All right, so let's work examples 2.1 and 2.2 in your book. And I am going to go over to here. And I have this little guy here. And we can do these problems. So I'll kind of set this up on a piece of engineering paper. All right, 2.1. I'll read the problem to you. The tank shown in figure 2.4, which is what I'm showing you right there, has a total depth of 25 feet of water in it. What pressure would be recorded on gauge A at the bottom of the tank? What pressure would gauge B at the height of 15 feet from the bottom indicate? Okay, so part A, pressure at A. Okay, so we're in English units. Pressure at A, so that is 0.43 times H. Okay? So remember, you always want to measure below the water surface. Right here at this point, the pressure is 0 as soon as you stick your nose above the water. So I'm measuring below that. All right, so the pressure at A is, so H, so we know from here down to 25 feet. H is 25 feet. So the pressure at A equals 0.43 times 25. And that, my units are PSI. So I'll take a calculator here. All right, so 0.43 times 25, and I get 10.75 PSI. So if I'm standing at the bottom of that, I get 10.75 PSI. All right, and then the second question is, what pressure would gauge B be at the height of 15 feet from the bottom? Okay, so remember 15 feet from the bottom, so I always want to measure from 0. So it's 15 feet, so that means we have 10 feet from the 0. So 2, pressure at point B equals 0.43 times 10, and that equals 4.3 PSI. So be careful when you read a problem. It says 15 feet from the bottom, but remember, I always have to start from the water surface down. Okay, so 15 plus 10 is 25, so that means point B is 10 feet down from the water surface. Okay, so that's that example. All right. Example 2.2, an elevated water storage tank and a connecting pipeline are shown in figure 2.5. So, oops. So here's 2.5, figure 2.5. I'll make this a little bit bigger. Okay. Uh, 2.5. Compute the hydrostatic pressures at point A, B, C, D, and E. So I need to compute the hydrostatic pressure at point A, point B, point C, point D, and E. Okay. All right. So we are in meters now. Meters. So our formula is P equals 9.8 times H, and we know H is in meters. Okay, so remember, where do we start? We always start from the water surface. So the pressure at A equals 9.8 times, okay, so we at water pressure is 0 is 100 meters, and point A is at 95 meters, so we need, this is an elevation, not a height, don't get those confused. So 100 minus 95, and that'll give us our pressure. 9.8 times 100 minus 95 is 5, so this is 49 kPa. So my pressure at elevation 95 is 0.49 kPa. Okay, now let's do the pressure at point B. So we're going deeper. So we're at elevation 70. So the pressure at point B equals 9.8 times, so we start at elevation 100, and then we go all the way down. So this is a continuous surface. There's no valves or anything. Continuous all the way down to elevation 70 meters. So that's 30 meters. Okay, so 9.8 times 30, so that's 294 kPa. Okay, you could also do what? Could you take this guy? You can also solve it this way, because we know the pressure at elevation 95 is 49 kPa, right? And we're going to add 9.8. So we need to go from elevation 95 down to 70. 95 minus 70. Okay. So 9.8. So 95 minus 70 was 25 times 9.8 plus 49. I get the same answer. Equals 294 kPa. So two ways to solve that problem. Okay. So I just like to start from the beginning at 0. All right. So the pressure at point C, well, is this connected? There's no valve in here. It's a continuum. It's continuous through. There's no valves in there. So that means the pressure at point B equals the pressure at point C. So that is 249 kPa. Okay? Because we're still, so even though, remember what the theory is, even though I'm standing, if I'm standing over here, or standing right at point B, or standing at point C, I'm still at the same elevation below the water surface because it is a continual medium. It does not matter that I'm not directly over the column of water. The pressure is still going to be the same. Okay. So pressure at point D. All right. So we know we are at, oops, that's a little sloppy there. So the pressure at point D equals, again, you can do it two ways. I'll just do the way that I like to do. 9.8, that's our times. We start at elevation 100.00 meters. And point D, we're at elevation 55, 00 meters, equals 100 minus 55 times 9.8 equals 400 kilopascals. That is the pressure at point D, pressure at point C, point B, point A. Okay. All right. Pressure at point E. This valve is closed, so that means my pressure is 0. Okay, 0 kPa. If I have a closed valve, it's just like opening a hose, right? You do not see any pressure. If there's no water coming out of your end of your hose, the pressure is 0. So 0 kPa. As soon as that valve completely opens, it's going to be, because it's at the same elevation as point D, and it's a continuum medium. Remember, there's no intersection. There's no interruptions in it. It's going to be the same as point D. Point D, pressure at D equals pressure at E when valve is open. Okay. All right. Back to our PowerPoint. So that's example 2.1 and 2.2. All right. 2.1, 2.2. All right, let's talk about pressure head. Way to express pressure in terms of meters or feet instead of kPa or psi. It is actual equivalent height of water above a point. Okay. So, what does pressure head mean? All right. So, we use this in geotechnical engineering. All right, or a lot of applications. So, it's called a piezometer. Okay, so what we do is sometimes what we'll do, we want to know where the pressure is. So what we do, so say I have a dam here, and then it's called a vibrating wire piezometer, and I have this vibrating wire piezometer at a known elevation below the ground. Let's just say 10 feet. Okay, I know this elevation. Let's just say elevation 100.00 feet. Okay, all right. So now it's going to read a pressure above that point. So say the piezometer is reading, what's this, 5 psi. Okay, so that means there's a column of water above that pressure reading 5 psi. So knowing 9.8, or let's do English, 0.4 times H equals pressure, or 9.8 times H equals pressure. This H term is what is pressure head. Okay, so if I know pressure, I can rearrange this equation. So P divided by 0.43 equals pressure head. Okay, so if I know I have 5 psi divided by 0.43, so that means I'm above my dam. That is, the water is 11.6 feet above that point. So that means I have an artesian pressure. But so basically it's another way so we can determine, let's just pretend it's below the dam. Okay. It's in the dam. So now I know I can determine a water table. So that's the H in these terms are the pressure head. So all you do, they have conversions in the book, which is just the inverse of these. If you just know this formula and rearrange it to solve for H or P, it makes your life a lot easier. Okay? So let's do 2.3 and 2.4 in your book. So I'll go back to my whiteboard. All right. Example 2.3. I actually kind of drew a picture here to help things out here. All right, example 2.3. A pressure gauge on an open tank of water at a point 5 feet above the tank bottom registers 13 psi. What is the pressure head at that point? What is the total depth of the water tank? Okay, so the question is, 1, pressure head. Okay, that's a question mark. So that's an H, and then that'll be in feet because we're in English units. And then what is it asking? Second question, what is the total depth of tank? Depth of tank. Okay, so let's answer number 1. So we know P equals 0.43 times H. Okay, I'm going to rearrange the equation. So P divided by 0.43 equals H. All right, so we know the pressure is 13 psi. Now be careful, you got to be in the units because number this has to be in psi. Divided by 0.43 will give me my H in feet. Okay, so 13 divided by 0.43. So I get 2.3 feet. Oops. 2.3 feet. Okay. So basically, okay. All right. 2.3B. So what is, okay. The pressure is 5 feet above the tank bottom measures what is the pressure head at that point. So we're 2.3 feet above that. Okay. I just want to just double check here. So using equation 2.8, 30 feet. I did something wrong here. The pressure on the gauge on open water point at 5 feet above the tank bottom registers 13 psi. So 13 psi. Let me take a look here. 13. I'm going to pause this. I'm going to pause for a second. Pause. Come on. Well, why won't it let me get out of there? Okay, back at it. Sorry, so I put the numbers in my calculator wrong. I was wondering why this problem didn't look right. So 13 divided by 0.43 is 30.23, so let's just say it's 30 feet. So we have basically the water surface above that is 30 feet. So answer to number 2, what is the depth of the tank? So we take 30 feet plus 5 feet, and that equals 35 feet. Okay. So sorry about that mistake. So you may have to fast forward through that. All right, next example problem. All right. Example 2.4. A sealed tank shown in figure 2.6, which you can see on your screen, has a pocket of air trapped above the water, which is 1 meter deep. So the water is 1 meter deep. A pressure gauge at the bottom of the tank reads 30 kPa. Determine A, the pressure head of the water at the tank bottom, B, The height the water will rise in a vertical tube if the valve is open, and C, the pressure in the trapped air. Okay, so, all right, so here we go. So what is it asking us to find? 1, pressure head at bottom of tank. So P, pressure, bottom of pressure head. All right, so you got to make sure you read the question carefully. All right. So we know P equals, so I'm just going to write, I know I'm in metric unit, Q equals 9.8 times H, okay? H equals meters, and I know H equals P divided by 9.8. All right, so 1, H at bottom of tank. Question 2, B, the height the water will rise in the tube. Okay, so I can just do this. This is question B. Okay, and C, the pressure of the trapped air. P. All right. So, with that, we have 30 kPa there. Okay. We know, so to find the pressure head, first you need to find the pressure. So the problem is, so this is C, this is problem A, sorry. Keep jumping around here. All right. So, problem A. P equals 9.8 times H. We know P, the pressure at the bottom of the tank is 30 kPa. Okay? So we're trying to solve H. So H equals P over 9.8, and that equals 30 kPa divided by 9.8, and that equals 30 divided by 9.8. So we get 3 meters. Okay. So, but if you notice, because there's 30 K, so that means there's some air pressure in here. Okay. So that means basically the pressure head of that water, it's, you know, this is, it's greater than 1 meter. It's 3 meters. That's because we're adding extra air pressure into there. Okay. So B, okay. So B basically, once I open this valve, is, let's see, A, the pressure head of water at the water at the tank bottom. So that is 3 meters. Okay. So we just also answered question B, because see, this is, the valve is open. This is continuing and nothing blocking it. So the height from here up is 3 meters. So because this is all connected. So we just, A and B are basically the same answer, because there's air pressure pushing on that. So we have 3 meters. It's going to go up because this is all connected. So answer to B is 3 meters. And then C is how much air, what is the air pressure? So P air plus P water equals what? Okay. Equals a total, equals a total of 30 kilopascals. So P air plus P water. So we know we have 1 meter of water, so that's 9.8 times 1 meter equals 30 kPa. So the air pressure P air equals 30 kPa minus 9.8 kPa. So 30 minus 9.8 is 20 kPa. Okay? Because this 9.8 times 1 is 9.8. So the air pressure we have is 20 kPa. Okay, I'm going to erase this so you can summarize everything. And this. All right. Okay, so we know P pressure equals 20 kPa. So 20 kPa plus 9.8 kPa equals 30 kPa. So that's the pressure at the bottom of the tank. Okay, so now because this valve is open, to calculate H, remember H is the same term as this right there. So I know this is 30 divided by 9.8. It'll rise 3 meters up into that piezometer because it's connected. So the pressure here is 30, the pressure here is 30, and here is 30. No matter where I'm standing, it's 30 kPa because it's open. So now I want to back, how high is that going to go up? I just solve for H and it's 3 meters. Okay. So, all right. So now that's it for this lecture. So what I'd like you to do is review Appendix D, read Chapter 1 and Chapter 2, read all of Chapter 1, and then Chapter 2, Section 2.1, pages 24 to 29, Chapter 1 review questions. So when you look in your book, there's actually review questions and practice problems. Okay, there's 2 sets. So Chapter 2 review questions, and then work Chapter 2 practice problems 1 through 5. So next week, Tuesday, I will chime on, and then if there's any questions on, we can review the homework, and then there will be a quiz on Chapter 1, or I'm sorry, Learning Plan 1, due next Friday. So if that's it, have a great day, and let me know if you have any questions.